Okay, so before I start going with the notes, I just want to describe the cell again here. A voltaic cell, sometimes it's named after Volta. Basically, it's a battery. Okay? But we talked about other cells before. There was primary cells and secondary cells. Do you guys remember those terms as well? Primary cell is like a single-use battery. Right? Like what's in your calculator is a primary battery. Once that battery is dead, it's not, you don't recharge it. Does that make sense? Whereas your cell phone runs on secondary cells. Well, that's kind of what I want to talk about today. The idea of we can actually recharge batteries. Okay? We can send electrons back from where they came from. Let's say the electrons went from here, anode, to here, cathode. Well, in a primary cell, as soon as all the electrons have gone from here to here, the battery's dead, we're done. But if you reverse things and add electricity and plug your phone into the wall, we can send the electrons from here back to here. Here's the problem. They don't want to do that. Hopefully I can try to describe that in this cell here. Imagine that you set up a cell where it was lead and zinc like this. That would be spontaneous. So then your lead turned into lead solid, your zinc turned back into zinc, and you'd say, well, now I'm stuck. Okay. Well, now what you really want to do is reverse this thing and find a way to make it so that this zinc right here turns back into that zinc, and this lead right here turns back into that lead. Basically, you need this stuff and this stuff to react. But should they? No. Well, they won't. Because based on oxidizing and reducing agents, this guy right here is the strongest oxidizing agent. This guy right here is the strongest reducing agent. Should this guy and this guy be able to react with each other? I'd say no, they shouldn't. Because this guy right here does not want electrons, and this guy right here does not want to give them up. You get where I'm going here? So in order to cause this reaction to happen against its will, we have to add electricity. We have to add a voltage. Well, it's actually not that hard to figure out how much voltage you require. You take those same two numbers and you subtract them. Only now we're going to imply that it's a negative number. See, if we want this guy right here to be the cathode, his number is actually going to be lower than this guy's number. Now let's actually just do it. Can you guys find me the number next to zinc? What is it supposed to be?
Is it -0.76?
Okay, and what's the number next to lead?
-0.13.
Okay, so normally this lead and this zinc would react with each other. And let's say it did do that, and it's reacted, and the battery's now dead. And so now what you have is this zinc and this lead, and we want these two guys to react. And I would say that this is non-spontaneous. It shouldn't occur. So if we add electricity, it'll cause it to happen. Well, you're subtracting the same two numbers, only you're subtracting the other way around. Now you're going to take the negative 0.76 and minus the negative 0.13. It'll be the lower number minus the higher number. And what you're going to end up with is a negative number when you're done. What this implies then is we need to then add this much voltage to make the reaction happen. Does that make sense? If you end up with a positive voltage, it means it's like a real battery and it's giving off electricity. If you end up with a negative number, it means that we can make the battery recharge if we add that much voltage back again.
So then by adding that much voltage, you can get it to recharge.
I can cause this zinc and this lead to react with each other.
So how do you know if it's that kind of cell?
Okay, so we'll know that it's this sort of cell because it's non-spontaneous. Does that make sense?
Yes.
So let me look at this slide right here. I'll just fix this here.
So it'll basically tell us what our anode and our cathode is, right?
You'll have to probably interpret that,
Yeah.
but yes. Like for example, let's say it gave you gold and iron. Is this a voltaic cell or an electrolytic cell?
Voltaic.
I'd say voltaic because it's going to give you electricity. Okay. Let's say that rather than having this gold though, that you had, or zinc, whatever, right? Would this stuff react on its own?
No.
Okay, so it's almost like this is a dead battery. But if we plug it into the wall and recharge it, we can cause this to go back to that and this one go to that, but we're going to need to input a certain amount of voltage. And if we add that much voltage of electricity, we can cause electrons to go back from whence they came.
Oh, question.
Yes.
So with however much voltage comes out of the little outlet,
Sure.
if there was more or
Still
less,
fine.
does that make
More-
it happen quicker or
No.
slower?
No.
Oh.
Voltage, if there's more voltage, not a big deal. If there's not enough voltage, that's a problem. But if there's more voltage, it's fine, but that won't cause speed. In terms of, you were in physics for this part here, voltage is about an energy difference, whereas current is about a speed.
Okay.
So it won't actually make it happen faster necessarily. Good question though.
Is the cell not, is this like the zinc and the lead together non-voltaic then? Or
Well,
they're both?
depends on which one you're talking about.
So
If
they-
it was this lead and this zinc, then it would be voltaic.
So then would the.
But then if it was this zinc and this lead, then it would be electrolytic. So like this guy and this guy is a battery, which would then form this guy and this guy as products, because this guy would turn into that stuff, this guy would turn into this stuff. So these are your reactants and reactants. This is your product and product. But now that you have this stuff and this stuff wouldn't react, but it could if you added electricity.
The products are just like that battery.
The products were the dead battery, right? So this zinc and this lead are the dead battery. But if we could recharge the battery, we could actually cause this stuff to turn back into this stuff to turn back into this stuff. But we have to recharge it basically.
That doesn't change the anode or cathode, right? Like it's still zinc solid.
Well, it does now, because originally this guy right here would have been your reducing, so he'd have been the cathode, and this guy would have been your anode. But then this guy now would become your new cathode, and this guy here would become your new anode. Let me keep going here, would you? Actually, while I've got my chart here, this allows for some interesting things, like say water. Here's water right here, and here's water right here. Would it normally react just on its own? And I'd say no, it shouldn't. It's not spontaneous. But if we run current through water, we can actually cause water to turn into oxygen gas and hydrogen gas. You guys ever heard of this before?
Yes.
Okay. How much voltage would it require? Well, from here to here is how much voltage it would require. So since we're trying to make this one go that way, this would be the reduction, which would be the cathode. And since this one is trying to go this way, this would be your oxidation at the anode. So you'd take your cathode, negative 0.83, minus your anode, which would be 1.23. So 2.06, but negative volts. Does this reaction happen on its own? No. But if you hook it up to a power source of at least 2.06 volts, you can actually make water turn into its elements of hydrogen and oxygen.
So that's all it takes.
Yeah.
So you have to 9-volt battery, you put it in water.
We could test this later today if you want. I can grab the stuff if you want. Just let me finish my lesson, I'll show you it. Yeah. No, not boiling water. Boiling water would be making it go from a liquid to a gas. This is actually decomposing water from like H2O as a molecule into H's as hydrogen gas and oxygens. Do you guys remember the terms from last year, inter and intramolecular bonds? It's been a while.
I remember hearing it.
I don't remember what they mean.
Okay, so here's some water molecules. This is a bond within a molecule. This is known as an intramolecular bond. Then there are attractions between molecules that keep molecules stuck together. They really aren't bonds in the same way because they're not really based on electrons. But if we call it a bond, this is known as an intermolecular bond. Okay. And in breaking intermolecular bonds causes you to go from solid to liquid to gas, because you're taking individual molecules and you're separating them. But if you break an intramolecular bond, you're actually breaking the bond inside the molecule, making this turn into, like, say, hydrogen and oxygen gas. This, if you break this bond, just makes it go from solid to liquid to gas. Okay, here's the point I want to make here. There is one purpose to these non-spontaneous electrolytic cells. Recharging batteries, I start with that because I think you guys all intuitively get that because you all have cell phones. You get that concept. 5 years ago, I didn't start with that because maybe that didn't apply. But nowadays, I think you guys all get the concept of live battery, dead battery, just plug it in and it's live again. And everyone gets that, right? But we didn't always have cell phones. This used to be one of the biggest purposes, trying to produce substances. Let's say that you want to produce, I don't know, what's a good example here? Let's say you want to make fluorine gas. Like, let's say you want to make fluorine gas. One of the ways you could make it, let me just erase some stuff. So this is your goal right here. What you could do is you could find some fluorine ions. You could find, I don't know, some cadmium ions. Would these things here normally react with each other? I'd say, well, no, they wouldn't. But if you add whatever this difference is right here, if you added a bunch of electricity, we could produce fluorine gas. So the actual production of elements is actually purposeful with this.
Okay, so I have a question again.
Okay.
So it goes from being like the proper thing, so spontaneous.
This way, yeah.
And then it runs out.
Sure. So
And
let's
then-
say it's over here and it's not going to react anymore.
And then you just add an amount of voltage that
So
you
if,
need.
so if you re-add that electricity, you could cause it to go from here back to there.
Okay.
Does that mean you can make any reaction work now?
Yes.
Okay.
Yeah. So for example, like this guy and this guy, they don't react with each other. I can force them to.
Okay.
Actually, this one's a good one to talk about, the one I just circled. Okay. Because this one, most people probably know about this as well. Let's say I gave you some chromium 2+ and some lead solid. Is this going to react?
No.
I'd say no. But if I add some voltage, I could cause this lead solid to become lead 2+, which is not all that purposeful actually. But what it would do is cause this lead 2+ to become chromium solid. And this has huge applications because we like to chromium plate a lot of things. For example, vehicles. Anybody have like chromium on their really expensive car? Who's got the most expensive car here? Like chromium hubcaps or no?
Shocked you
No? Oh, okay. What is like a
Trent's got chrome on his car.
you got like because that's like the high price kind of thing, right? Because it won't rust anymore. Anyways, the producing elements is probably the more important thing. We can actually cause non-spontaneous reactions to happen, which would actually like plate the outside of certain objects. So if you ever hear of like gold plating something or chromium plating something, that's kind of what we can do with this, is we add electricity and force all of the electrons to cause a reaction to happen. Let me keep going through my notes. So here I've got a diagram here of the exact same thing, only there's one main difference. Up at the top here, normally I drew an iPod to kind of represent that like something was happening. On the diploma, they will draw a power source of some kind. That is the indicator to you that this reaction is not spontaneous on its own and that it will happen, but if you add a battery. Normally, which way do electrons flow? Well, normally they flow from the anode to the cathode.
What?
Okay.
Oh yeah, sorry.
And they still are. Only now it's going to flip. Now we're going to call our anode the positive and our cathode the negative. That is the biggest twist here. Electrons will still go from anode to cathode. But this guy used to be, like the electrons used to go this way. Does that make sense? Like the electrons wanted to go away from this negative and towards this positive. That's what they used to do. But now we're going to force them to go back against their will. So this was like natural. And then the battery is going to force the electrons backwards. Okay. So by definition, we still say that electrons go from anode to cathode. So this guy right here is now the anode. This guy right here is now the cathode, but the big switch is the positives and negatives. Anodes are now positive, and cathodes are now called negatives. Yeah.
So it used to
and
be
that's what you-
no.
So like this guy here used to be negative, and the electrons went over here. So this guy used to be the anode, and this guy here used to be the cathode. But now that it's an electrolytic cell, they have to flip so that we can send the electrons back the other way.
So the names of them don't change, but you need to
Change the sign.
the sign of them.
Yeah. So the sign changes if it's not spontaneous.
So if you see something like this on the diploma or on a test or something, and you see anode with a positive, then it'd be like, is
That'll be
this
your tip.
whatever, or is it natural?
Yeah, so you'd say either it's spontaneous or non-spontaneous,
Okay.
or you'd say is it a voltaic or electrolytic. So this is an electrolytic cell because electrons wanted to flow this way, but we're actually forcing them to go the other way.
Okay,
What if
so
they-
you're, oh sorry, go ahead.
What if they didn't actually tell you it was anode cathode and gave you like,
Mm,
would they do that?
they'd have to give you some sort of information to help though, right? Like that's going to be a big part of what they're going to test you on is interpretation. I'll show you some questions in a while.
So our phone chargers are electrolytic cells.
Well, your charger basically makes your phone an electrolytic cell, and then when you take it out of the charger and you run your battery, then it's a voltaic cell. So your phones actually really do both, right? Right now, it's a voltaic cell. But as soon as you plug it in and charge it, well, now it's being an electrolytic cell, causing electrons to go back from where they came from.
Okay, so chargers and volts just make it electrolytic temporarily kind of thing?
Sure, until you want to then use it as a battery again. Okay, so here's just a lot of notes about the two types of cells. Voltaic cells take chemicals and make electricity. They react spontaneously. And the cathode is always above the anode, meaning that your voltage is positive. The electrolytic cells are almost the exact opposite. These require an outside power source.
Sorry, what does it mean cathode above anode?
Oh, so like when you do your chart here, it goes from here to here. Your cathode is above your anode because cathodes go this way doing reduction and anodes go this way doing oxidation. Does that make sense? Whereas in an electrolytic cell, it's the opposite. You'll have a cathode down here and an anode up here. This reaction should not happen, but we're going to make it happen by adding electricity. So it needs an outside power source. The cathode should now be below the anode. So this up here will be your anode. This will be your cathode. One thing here, because of the fact that we're adding electricity, you don't actually need a salt bridge. We're not worried about the cell becoming polarized because we're forcing electrons to go against their will anyways. So it's not actually that big of a deal. And it basically takes electricity to make a chemical change. I mean, here's a chart that more or less summarizes all of the differences between them. Most of them are different. There's a few similarities. This is spontaneous. This one's not. This one, the voltage is positive. This one's negative. Here, the cathode is positive, but then here, the cathode is negative. Here, the anode is negative, but now it's positive. Here's where it's the same, though. Electrons always go from anode to cathode. I don't care what cell it is. Electrons always go anode to cathode.
You just change your negative.
You just change the negative sign, that's all.
And then always will. Right.
So yeah, this one you can say always. I got more stuff you guys can read, but why don't we do the example and then I'll call it a day. Read through the rest of that stuff if you want. It basically talks about how we hook things up and positives and negatives and flipping things. Okay, here's an electrolytic cell. There's going to be a power supply, so I'm going to hook up like a battery. And it's connected to two nickel electrodes. So over here, I have an electrode of nickel. And over here, I also have an electrode of nickel. We actually only need them to be in one cup now. We don't actually need two cups because the salt bridge isn't relevant. Okay, here's what's in the aqueous solution. We've got cadmium nitrate, so that means you have cadmium 2 plus and NO3 minus. And we also have zinc nitrate. So we have zinc 2 plus and NO3 minus.
So can you send this out?
We're going to do a lab on this
Yeah.
next week, 2 weeks Monday. We're going to test all this stuff. Sorry. You're not here that day? I'll try to do a demo after you guys come back from a break, maybe. It takes a long time to set this stuff up. So, okay, we want to try to figure out the minimum voltage required to make a reaction occur here. So, let's talk through what we've got. I need to find one of those sheets. I don't have one nearby. Okay, so what do I have in my beaker of stuff? Nickel solid. We also have cadmium 2 plus. We have zinc 2 plus. We do have NO3, but NO3 doesn't react unless there's a hydrogen plus nearby. We don't have any hydrogen. So I guess the nitrate is a spectator ion. Okay, so as we currently have here, is there a reaction occurring? I would say no. No, there is not. Because we don't have this hydrogen right here, so therefore that's kind of useless. So is there a spontaneous reaction? No. Okay, but I could make a reaction occur if I add some voltage. Let's say I add 0 volts. Nothing will happen. Let's say I add 0.1 volts or 0.2 volts. Nothing might happen until I get to whatever the difference is between these two values here, which looks like it's, that'll be the first one that happens. So if I were to add, what's the difference between this nickel and that cadmium? 0.14? If I add at least 0.14 volts, I can make this reaction happen. Okay, here's the problem though. I don't want to add too much voltage. Because if I add too much voltage, I could also cause this zinc to react as well. So sometimes you have to add like more than an amount of voltage for one, but not too much if the other guy also reacts. How far would it be from here to here? 76 and is that 26?
0.5.
Okay. So I guess what I'm trying to say here is I need to add more than 0.15 volts, more than 0.14 volts, so that this stuff reacts, but I don't want to add more than 0.5 volts because then the zinc would also react. Does that make sense? So maybe what I would do is I would add 0.25 volts. And if I did that, where's my picture now? I could cause the electrons to go against their will. So then the cadmium 2 pluses would start to form some cadmium solid. Cadmium 2 plus would pick up some electrons and form some cadmium solid. And what you would see at this electrode right here is you would see a coating on the outside. Basically, you'd be cadmium plating this electrode. That makes sense? So when I talk about things like chrome plating or cadmium plating or gold plating, that's kind of what's happening here is we're making the outside of this nickel object covered in cadmium.
So is the minimum just the difference between cadmium and nickel?
Well, it has to be at least between cadmium and nickel. The only problem is I don't want to go too far because I don't want this zinc to react.
Well, then wouldn't you just do the 0.14?
Sure, or 0.15 or 0.16 or 0.17, but I don't want to make it 0.5 or 0.6 because then I'd also get some zinc on the outside of this guy. And maybe I don't want zinc on the outside. Okay, what's happening over here then?
Is that disintegrating?
It would be, yeah. This thing would then be disintegrating because
It loses electrons.
it's losing its electrons. It doesn't want to lose its electrons, but we're forcing it to.
So it's becoming nickel 2 plus.
Good, it's becoming nickel 2 plus. So this would become nickel 2 plus. So then your nickel solid would become nickel 2 plus and 2 electrons. And you need a minimum of 0.14 volts to make this happen. We can go with more than that, but then expect multiple reactions to occur. Often what happens when we do a lab with people, is they crank the voltage to like 12 volts and say, hey, the reaction's bound to happen, it's 12 volts. But then you actually end up having like lots of other reactions happen that you didn't want to have happen. Like for example, water will actually start to decompose as soon as you add a few volts into it. So this is one of those times where it's like you don't want to say more power, it's better, right? You kind of want to limit it.
So which is the anode and cathode then?
Okay, so let's talk through that. This guy right here is gaining electrons. So if this is gaining electrons, it must be the cathode. So over here is the cathode. But we're going to designate it as the negative sign though.
It's gaining lead.
Well, we flipped compared to what we're used to. This is the negative side of the battery basically.
Yeah, I don't understand.
We basically, to keep the two cells straight, we would flip the positive and negatives. That makes sense? So like, when we were first talking about voltaic cells, positives and negatives, we basically said cathodes are positive, anodes are negative. Well, when you're now hooking this up to the power supply to like recharge your battery, basically we flip the signs basically.
Because you want
Because-
positives to go over to the cathode?
Well, because what we need to do is we need to have the negatives go this way here. And so the negative, the electrons are going to come from the positive side of this battery through the battery over to here. Does that make sense?
The positives are or the negatives?
Well, negatives are moving. Because electrons are moving from here to there. Like our electrons are going this way. But the reason that they're going this way is because of this battery. So what you have to do is you have to hook the negative side of the battery up over here and the positive side of the battery up over here so that the electrons go away from this negative over to here. So that's why we call this the negative now instead. So it's kind of backwards than what you're
But
used to.
yeah, it's like it's the cathode
Okay,
that's
so-
making it negative.
Because of this side of the battery being attached to it. Because the only reason that this is occurring is because of a battery. So really, we're changing the positive and negative based on the orientation that we put the battery in. If you took the battery and flipped it the other way, it wouldn't work. Does that make sense? Like if you put the positive side of the battery here and the negative side of the battery here,
One recharge.
it wouldn't recharge. But if you put the negative side of the battery here and the positive side of the battery, it would recharge this thing. That makes sense? So that's what this negative here is an indicator of. It's the indicator of which side the power supply is being attached to.
But not like
Not the anode or cathode.
So don't think of it as like which way the electrons are flowing. Just know electrons always flow from anode to cathode. So the electrons are always going to show up at the cathode, but we're now going to call it a negative. Maybe a good way of putting it is that should this thing have all these electrons? Normally it shouldn't. We're forcing them all to be there. So that's why we're going to call this thing negative.
So it's like you're forcing negatives to be with negatives when they're not.
Even though they don't want to be. Maybe that's a good way of thinking about it. The electrons wanted to be over here,
Yeah.
but we're going to force them to go against their will and show up over here. So that's why we're going to designate this guy as a negative now, and this guy as a positive.
Makes more sense.
Does that work?
I think so.
Okay. That's all I got. It is really, I don't want to say straightforward because it makes it sound simple, but you need to know the difference between these two. Why don't you guys go take a 5-minute break? I'll go grab some chemicals and I'll see whether I can make some cells real quick. Show you what this looks like maybe. So go take a 5-minute break.